Any questions before we get started? Like, we covered quite a bit, and let me start today by saying we're going to cover a lot of material. I'm going to go really fast. It's just to expose you to it. You don't have to know it all by the end of the lecture. It's your first time through it. We're going to be working on this for a couple of weeks before we get to the test. We're going to cover all kinds of material. It's going to seem overwhelming. It's not. Okay? But that's my little caveat. And I can hardly wait till I can take this thing off and talk like a human being. I gotta tell you. It's just about to my last mask. Is that gonna be our new phrase? I'm down to my last mask. Wow, like nobody even liked that one at all.
I laughed inside.
All right, so no questions. We're ready to go. Let's go. Right, I believe this is where we stopped. We were doing natural abundance, right? How do we tell the mass? Why is there an average mass and why isn't it just a whole number if the mass of an element is just the number of protons and just the number of neutrons added together? Because you can change the number of neutrons and when you change the number of neutrons, you change the mass. You make it different isotopes. Lots of elements have different numbers of isotopes. We covered that fluorine only has one isotope, and that's why it's good to be able to use for separation and like hexafluoride. So I believe we covered this already, but I'm going to go over it again. So to find the atomic mass average of all of 100 atoms of one element, you would take 98%, 0.892 at 12 AMU, and then you have the abundance of 13 carbon, which is the mass, right? Which would be 6 protons and 7 neutrons, and that would be 1.108 at 13.0035. You divide the percentages by 100, that gives you 0.98888. That's as many eights. 0.98892 times 12 plus 0.01108 times 13.0035, which gives us an average of 12.0111, and we usually see that on the periodic table as 12.01. Isotope masses are usually integers. Why? Because you have whole numbers being added together. The average mass is usually not, because you have different percentages of whole numbers being added together. And this is where we stop there. Silicon is composed of 28 silicon, 29 silicon, and 30 silicon. And the average atomic mass is 28.0855. What is the most abundant isotope? Just by looking at that. Would it be 30?
Is it just the higher number?
Yeah, so if it was 30, well, if we had more of 30 than anything else, what would the average mass be close to?
Closer to 29 or 30.
Yeah, exactly. But since the mass is 28.0855, most of the silicon is silicon 28. And how do we determine the relative isotope abundances? Well, in the old days, they didn't do it this way, but now we do. We use a reverse cathode ray tube. We form positive ions, observe bending in electric or magnetic field that depends on mass. So this is called mass spectroscopy. And this is a great instrument because it knocks off one charge and we get to find out what the mass is. So different isotopes have different masses. So when you get your weights of each thing that, each fraction that comes off the cathode ray tube and it gets to the collector, you can separate them. So here's a mass spectrum fingerprint of mercury. So you can see that the greatest fraction of mercury is at 202, and then 200, and then 201, well, 199, 201, and 198, and a little bit at 204. So that's the 1, 2, 3, 4, 5, 6 isotopes of mercury, right? And it makes sense, right? That it's pretty close to 200 because you have more below 200 than you do above 200. and there's mercury right there. In case you didn't find it, it's a D10 metal. So all the transition block here, these transition metals, they go to D10. We're gonna find out more about the D level and the S level and the P level coming up. So what about chemical formulas? Chemical formula notation. We use the element symbol like Hg and the number, right? The subscript is the number. The element symbol is the large capital letter here, and they're always integers. That's the beauty of the periodic table and elements and the construction of compounds. It's always whole number ratios. It's not 1.74 of this to 3.625 of that. It's 1 to 1, 1 to 2, 1 to 3, 3 to 5, right? Whole numbers. We call those numbers the stoichiometric ratios, right? Molecular formulas, actual numbers of each element in the compound. Empirical formulas are the relative numbers of each element. So you divide by the subscripts, the largest common factor. So, for example, I'll break out this collection of brand new pens that someone was thoughtful enough. Now, if somebody would just donate a mass spectrometer to this like department, we could do some chemistry. All right. So if we had, let's say we had PaO20, right? That would be in the correct order, and then also that would be the molecular formula. But if we divided this by the largest common denominator, which would be 4, we get P2O5. That would be empirical. So molecular, empirical. So the molecular is the actual ratio of elements to each other for the compound. The empirical is the smallest whole number ratio, right? And that becomes important because of the way we used to classify materials. Now we don't classify materials that way because we do better, we have a better ability to measure the molecular mass through mass spectrometry. But in the old days, you would have an empirical formula and you had to, when you got your chemical or compound analyzed, they would break it down and tell you, oh, it has this ratio of phosphorus to oxygen. And then you'd have to find another way to get the molecular formula. And we don't have to do that anymore. Thanks to mass spectrometry. So, hydrogen, H2 is an example of a chemical formula, oxygen, O2, water, H, the little space filling model, H2O, hydrogen peroxide, H2O2, carbon monoxide, carbon dioxide, right? Methane, carbon being the black space filling model, and then the bubbles on hydrogen, 4 hydrogens, ethylene, 2 carbons. This would be a double bonded compound with 4 hydrogens. One thing you should know about carbons is they always have 4 bonds. There's been a recent rumor that somebody found a way to have more than 4 bonds to carbon, has not been verified elsewhere. But it is going around the internet. You can say chemical formulas out loud, but be careful how you say them. Can I take your order? I'm a chemist, I will just have some H2O. Low, I'll have some H2O2. Here you are, gentlemen. Drink, thanks, thanks. Drink, boom, idiot. Because he had hydrogen peroxide. You can drink small amounts of hydrogen peroxide, people do it all the time for all kinds of weird reasons. But you don't want to drink very much of it. Many different ways to depict and describe molecules. We have the empirical formula, again, the smallest ratio of the elements. So CH, the molecular formula, what is that, C6H6, and then the structural formula, which is the rings compound. Here we have benzene, common concert cancer-causing agent that we used to wash our hands in back in the day. Not me, but the guys before me. Ball and stick model, and then the space filling model. And you can see they're all different representations of the molecules. So acetylene, CH, turns out it's a triple bonded molecule. These lines represent bonds between elements, right? And they represent kind of the shape of the molecule. The space filling model gives us the better shape, but we have to remember that's not really what it looks like. This is the area that's mathematically calculated to show the probability of what's there. So when we say this, inside this ball, there's a little tiny nucleus, right, with all the positive charge and the neutrons. And then in this area, the electrons are somewhere, right? That's the wave calculation that we do later. We may even look at it a little bit this semester. All right, glucose is that simple 6-chain sugar that is very helpful in creating energy for us. Ammonia, it's very smelly. We use it all the time. Another space filling model. So those are the things we have to be aware of. An empirical formula, the smallest whole number ratio. Molecular formula, the actual ratio of the elements for the compound of interest. We can depict it with a structural formula, a ball and stick model, or a space filling model. So structural and spatial isomers. What's an isomer? Same formula, different arrangements of atoms. So isomers have similar chemical formula, but not necessarily the same arrangement of atoms. So structurally, that means like you have, well, I'll give you an example here. Structural isomers, we have acetic acid, which is C2H4O2, and methylformate, which is another isomer, but this time it has the oxygen in the middle between the carbons, right? That's the difference in the structure, but they have the same formula, C2H4O2. So that's a structural isomer. Note, often grouping formulas in a more informative order helps. Acetic acid is better written as CH3CO2H, and sometimes it is, right? So spatial isomer is the same formula, same arrangement of atoms, but different orientation in space. And you can do that with model kits, and we'll look at that. So some spatial isomers, we give them a plus and a minus sometimes, an L and an S, an R and an S. They're also called optical or mirror isomers because they're rotated 80 degrees. Really blown up during class. That's nice. Hold on a second.
Can you go back to the last slide real quick?
Sure.
Got it.
Right, and so the COC bond is better known as an ether, and so when we're looking at these spatial isomers, it's the same formula, the same arrangement of atoms, but when you put them together, they're just, one's going towards the board, one's coming out of the board, kind of like that. And it's interesting, they have different smells. It's the same molecule, but they have different smells because they're because of the orientation of the atoms. Right, so anywhere where you see, so here's something that I don't know when we'll cover this, but if you see a double bond, that fixes the rotation. So this bond right here, a double bond, you see two lines, double bond. We'll talk about what that means later, but it can't spin now. It's fixed. So all the time, molecules are moving. Everything's always moving, vibrating. That's what the home page on Canvas is. It's a bunch of molecules all moving in all the directions molecules move. But one of the things they can't do is spin with relationship to each other like a single bond can. So if you have a single bond, you can do all the spinning you want. You fix the rotation here, but you don't change this movement or that movement. You just don't spin anymore, okay? And then if you have a ring, now that also limits. So if we put this in a ring, it looks like a ring, right? it limits the movements as well, right? There's some flexing, and we'll talk about that maybe later. Okay, so we've got all these things tied together, right? We know elements form compounds, and that we know the number of protons and the number of neutrons, but how do we put them together, right? Well, we put them together by the number of protons, and we found out there's an order to it, and it's a recurring order, and that's the period, goes across the period. So chemists notice the properties often repeated about every 8 elements, and that's called the rule of octaves or the octet rule. But in 1863, we only knew 56 elements. So 150 years ago, 60, 170 years ago now, we were only 56, and now we're at 118. So this guy, Dmitry Mendeleev, wrote a textbook, and he lined up the elements the best he could at the time. And you'll see, like so, here's some helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then spaces, like all these spaces in here. Right? And he predicted that there should be molecule elements there, and there weren't. That's the best part. So he only had 56 to choose from, and he spread them out so that they would repeat and be the same, right? And have similar properties. This turns into lithium, potassium, rubidium, and this isn't quite right, because this is a +2. But sodium, these are all +1s. They became the alkaline earth metals, and we fixed that a little bit better, but he had it nailed in the beginning. So the modern periodic table is this one. This is the one I usually throw in the back of the test, but you can still use the one that's handed out, and that will just be an extra one on the back. So periods, that's the horizontal rows, right? So repeating, filling a shell is the period. So we have some shells. The first shell we want to know about is the S shell, and it only holds 2 electrons. So these are based on the number of electrons, even though they're listed by the number of protons, right? So this would be the S orbital. It can hold 2 electrons. And then S orbital now becomes from here to here because it only holds 2 electrons. But we'll talk about that more too. So first row, period, second period, third period, fourth period, fifth period, sixth period, seventh period, and then you get to go home. We're also in order of increasing atomic number, right? Atomic number is the number of protons, always increasing. 1, 2, 3, 4, 5. So anytime you are given a number of protons, you know what the element is because the top number 24 matches the symbol, right? You change the number of protons, you change the element. What else? Okay, this little step-like line here, these are the metalloids, and they're right on that line. Boron, silicon, germanium, astatine, antimony, and tellurium. Okay. Sometimes this is arsenic, I should say, and astatine. Sometimes these are astatine is sometimes considered that. And we also, so these can be metals or non-metals, basically, depending on what they're reacting with. The non-metals are right here, and I learned something today. You know what? If it's not in this group right here, this green group of non-metals, guess what it is?
Metal.
It's a metal. I never thought of it that way, right? I always just looked, oh, it's in the metal section. Oh, it's in the non, but really all you have to do is look in the non-metal section. So pretty excited by that discovery that was shared with me today. And then this lower level are called the actinides and lanthanides, based because they're in the lanthanide and actinide series. This would be the f orbitals. So these are the d orbitals, these are the p orbitals, s orbitals, and you can put that over your group, right? These two groups, so going down as a group, going across as a period. This is the s portion of the periodic table. This is the p portion. This is the d portion, right? And transition metals. And then the lanthanides and actinides are the f portion. And you can see from that breakdown that the s has 2 electrons. 1, 2, 3, 4, 5, 6. The p has 6. The d has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 for F. What else? Groups are also called families, and each column has elements with similar properties. Again, atomic number, number of protons, atomic symbol, it's the letter or what it's called, and then the atomic mass is the number of protons plus the number of neutrons, and then that's an average based on the different number of isotopes that you have. So my boss was at Berkeley, so all the slides that we built had to talk about Berkeley. Anyway, the first isolation of acetine, experiment at Berkeley. So, and basically most of the new elements that have been discovered over the last 30 years have been at Berkeley. Lawrence Livermore Lab. Fun fact. So they had bismuth 209. Remember we said that a helium nucleus, right? Helium is just 2 protons being spit out. Well, bismuth, right? From Pepto-Bismol, by the way, has bismuth in it, bismuth sulfate. Bismuth itself can spit out a helium nucleus or an alpha particle, right? And it makes traces of acetine. So fed it to a guinea pig, they harvested the thyroid.
Oh my God.
Yeah, so back in the day, these guys, so this is one of the things about these people, right? Their ethics aren't the same as normal people's ethics, right? And they were isolated from normal people, so they would do these things. And then when normal people found out, they kind of put the brakes on this kind of,
Behavior?
yeah, whatever, however you want to call it, right? Torture is what I call it. But anyway, they extracted thyroid in the hopes of, learning something. And they got this acetine, which is a rare element. So look at how much there is, right? 1 ounce at any given time. So we don't use it for anything. You can exploit similarities in element groups. Acetine is similar to iodine. So it has similar properties, but we don't use it because there isn't very much. And it's also radioactive. So when there's 1 ounce, 7 years later, there's a ½ ounce. Okay. That's what that means. It's not like the half-life of the drug, which is a little bit different. Okay, so areas of the table have special names. Column 1 are the alkaline metals, right? They all have a +1 charge because they tend to lose 1 electron. Alkaline earth metals have a +2 charge because they tend to lose 2 electrons. The D block are the transition metals. Again, the F block are the lanthanides and actinides. Then we come over here and we have the pnictogens, right, which is, what is that? 1, 2, 3, 4. So 8, 7, 6, 5. So this is nitrogen, etc., right? The chalcogens, which is oxygen and sulfur, and the halogens, which are fluorine, chlorine, bromine, etc. And then finally the Nobel gases, which have 8 electrons in their outer shell, and they are the noble gases, like xenon, krypton. So metals and nonmetals are major categories to know, and we have some pretty pictures of metals like iron and copper and aluminum and silver and lead, and gold. And then bromine is a liquid gas combination at room temperature. You put bromine as a liquid, and then carbon and sulfur and phosphorus, all nonmetals. Right. Interestingly enough, carbon is not a metal, but it does form diamonds. Okay, so what else do we need to know? Yeah, that's about it. Okay, the alkali metals, lithium and sodium, so that's all column 1. Again, column 2, alkaline earth, oxygen, sulfur, selenium, chalcogens, halogens are, this is not for halo, right? This is not the same game. Fluorine, chlorine, bromine, iodine, acetine. Noble gases, helium, neon, argon, krypton, xenon, radon. So, name the third lightest halogen. So that would be bromine. Right, so you look on the periodic table, you look at the masses, right, and third lightest. It's a weird way of doing it. What is the common group name for element 38?
Alkaline earth metal.
There we go. Strontium in the second column, so it is an alkaline earth metal. And it also has what charge when it forms a compound?
+2.
+2, very good. Classify the following elements as metals, nonmetals, or metalloids.
Iron's metal.
Iron. Which of these are a transition metal? Where is iron? It's number 26.
Yeah. So the transition metal.
Transition metals, right? It's in the D block. D block is always transition metals.
Is that
Lithium.
Yes.
Lithium are +1 fan, so it's in which column?
It's an alkaline metal.
Alkali metal, column 1, right? Dom, you're out. You've already answered pretty correctly, so you're gonna have to wait till anyone else catches up. Tin. Is it a non-metal?
No, it's a metal.
It's a metal. And is it a transition metal?
No.
No. Okay. But tin is a funny one. It can be either tin 2 or tin 4, so it doesn't follow the general rules that we have that so it gets the same transition metal Roman numerals when you name them in the compound. What about sulfur?
Non-metal.
Non-metal. What about krypton?
Non-metal.
Right, noble gas. Silicon.
Metal.
Metalloid. Hafnium. I always wanted to make something with that, but I never did.
Metal.
It's a metal.
Metal. Okay. So that was fun. Oh, look, here are the answers. Krypton is not a metal. What the heck? Who did that? Oh, okay, that's the end of that slideshow. I gotta fix that one. Okay, let's see. We're gonna keep rolling now. Got another one. And we're not doing any group work, anything unless you have a question. Okay, so, where are we? 210, is that this one? Yeah, here we go. Okay, so we've introduced everything we need to know to make compounds now, right? We know how to measure things, we know how to report significant figures, we know how to calculate protons, electrons, atomic mass, number of neutrons, right? The number of neutrons is just the atomic mass minus the number of protons. We know about ions being the loss of electrons or the gain of electrons. We know that metals donate electrons, and those nonmetals receive, Super Bowl. Anyway, So let's talk about what we do to make compounds. Okay, remember how to do the slideshow. Okay. Slideshow. Alright. Not all compounds are molecules. Oh, here we go. Molecular and ionic compounds. Fact one, some atoms readily lose one or more electrons to form cation meows. Right? Some atoms readily gain or one or more electrons to form anions. So ionic. Actually gaining or losing. Taking that electron that belongs in the sphere of one atom and giving it to another, or taking one from the sphere of another. And nonmetals tend to. So here's some cation examples. Hydrogen loses one electron to form H+. And remember, H+ is just a proton. So interchangeably, people say H+ or a proton. Sodium loses one electron, forms sodium+. Aluminum loses 3 electrons for this class, and it's always 3+. Anion examples. Hydrogen, that sneaky hydrogen, can actually gain an electron too and become H-. These are hydride compounds. You'd see something like sodium hydride, and the reason you know it's a hydride is because the H comes second and the sodium metal comes first. Chlorine can gain an electron. Remember, all the halogens are nonmetals, they can gain electrons. Nitrogen, the nicotinide, is 3+, gains 3 electrons, N3-, and we call that nitride, right? When it comes at the end, we change the ending of the element from its regular name, like hydrogen to hydride, nitrogen to nitride, bromine to bromide. Some molecules readily lose or gain one or more electrons to form polyatomic cations meow, or polyatomic anions respectively. So polyatomic ion examples are ammonium, H3O+, hydroxide, cyanide, sulfate, phosphate. Fact 3, cations and anions combine to neutralize charge. There's the key. Neutralize charge and form ionic compounds. So the electron is going from the cation to the anion, and that's what holds them together. And then they form this molecular body that we're going to look at, and these ionic compounds. So the ratio you can see in the space-filling model, that you can see 1, 2, 3, and then this chlorine molecule. And then this chlorine molecule is surrounded by 1, 2, 3, 4, and then there's one below, that's 5. But this one is surrounded by 6. So we'll just learn more about the way crystals are formed later. So we've gone over common polyatomic ions again, but let's just hear them and say them. Hydrogen sulfate, HSO4, 1-, sulfite, SO3, 2-, hydrogen sulfate, HSO3-, phosphate, PO4, 3-, hydrogen phosphate, HPO4, 2-, and there's a related acid to all these, right? What's an acid? An acid is a proton donor. So what's a proton? H+. So if it can donate H+, it's going to be an acid. And sulfuric acid, well, this is sulfurous, but it can donate what? 1 proton or 2 protons, right? 1 to form hydrogen sulfide, and then a second to form sulfite, right? Then phosphoric acid has 3 protons it can donate, right? 1, if it donates 1, it forms dihydrogen phosphate, which is a -1. If it donates 2, it forms hydrogen phosphate, the 2-, and if it donates all 3, it forms phosphate. But you can have phosphate, the anion, without having had it come from phosphoric acid. Right. Perchlorate, ClO4, chlorate ClO3 minus, chlorite ClO2, and hyperchlorite ClO minus. That's a great one to learn, right? Because it's just an iteration of 4, and they're all -1, so I like to make compounds with those. Chromate CrO4 2 minus, I like to make either a compound with chromate or dichromate on the test. Permanganate, MnO4. These two are transition metal complexes, right? And ions. And we're going to get into how you calculate why these are 2 minus or 4 plus or whatever.
Question.
Yeah.
What chromic acid used for?
Beats me.
Okay.
But we used to use it a lot for plating
Yeah, that,
in the old days.
yeah, chromic acid.
For chrome,
Yeah.
right? And you
Not
also
sure,
used it,
right, not so.
Kodachrome, we also used it for film. But we found out that people get very afraid of certain charges of chromium, and the public can't really differentiate between chromium, the element, chromium 5 plus or 7 plus. They can't handle it. So, and then the government even, sorry government, has even more trouble. They weren't forced to take years of chemistry, I guess. All right, ionic compounds, right, which means cation and anion. Wow, we add to our list of pure substances. Right. So remember how this works. The pure substances are either elements or compounds, and elements are either atomic or molecular, right? O2, there's 7 molecular elements that we should know. Have no fear of ice cold beer, right? If you had my class, you heard me say that a lot, and I tested you on it. So, hydrogen, oxygen, fluorine, chlorine, bromine, iodine, nitrogen. Okay, 7 show up as molecular elements. And then the rest are just atomic. They exist as just by themselves. And then we have compounds. We have molecular compounds, which share electrons, and ionic compounds, which are a combination of a cation and an anion. Formula units. Empirical formulas for ionic compounds. Ionic compounds have been distinguished as non-molecular now, right? So they have a formula unit. Sodium chloride's formula unit is NaCl. Right? They don't call them molecules anymore. It's one way to confuse people even with greater degree of certainty. All right, which atoms form cations, which form anions? Anions. Atoms lose or gain electrons to achieve the number of electrons of the nearest noble gas. Okay, why? Because noble gases are stable. And for the longest time, we couldn't even make a compound with a noble gas because it took too much energy to remove or add an electron to it. But we do now, every once in a while, make some. If we look at the metals, right? All cations, cations. Here's some common. This is 3 and 6, but 5 and 7 are also available. Plus 2, 2 and 3, 2, 2, 1 and 2, 2, plus 2 plus 2 plus. These are common, but it doesn't mean that's all that's available. It's just the common ones. And then aluminum is usually 3 plus. Carbon can be at the end and be an anion and be a 4 minus. And they call that, so carbon to carbide, nitrogen to nitride, phosphorus to phosphide, arsenic to arsenide, tellurium to telluride, selenium to selenide, sulfur to sulfide, oxygen to oxide, fluorine to fluoride, chlorine to chloride, bromine to bromide, iodine to iodide, acetine to acetide. But who makes those? There's only 1% of those available anyway. Then we have helium, neon, argon. But what's going on here? These go, so this first row goes to 2. So some compounds are stable with 2 electrons. So those would be S compounds, right? Then 8, so 1 to get to 8, add 2 to get to 8, add 3 to get to 8, add 4 to get to 8. Nitrogen is a funny one because it can lose 5. 1, 2, 3, 4. Is that 5? Oh, this one too. 1, 2, 3, 4, 5, and now it's here, right? And then what else do we have? Phosphorus adds 3 to get to 8. Arsenic adds 3 to get to 8. Tellurium adds 2 to get to xenon. Okay? These two lose. If this loses 2, it goes back to the row above it, right? Configuration, the stable configuration of radon. If barium loses 2, it goes to xenon, right? It has the same electronic configuration, right? The same number of electrons, and that becomes stable. Ionic bonding. Simple ionic compounds occur between metals and nonmetals, which form metal cation meows and non-metal anions. We call which elements are metals and nonmetals. So apparently we make a big distinction, right? We expect you to know the difference between a metal and a nonmetal. And again, if you just look at this corner and it's not there, it's a metal. So easy. I had no idea. Okay. Molecular bonding are usually composed of nonmetals only. Discrete numbers of connected atoms, not infinite arrays of ions. Right? So a molecule is discrete. It's just that package. An ionic compound forms layers of itself over and over and over again. Where molecular compounds occur? Ooh, look at that little Bermuda Triangle there. So remember, the metalloids count as either metals or nonmetals. So this group right here often forms molecular compounds. And when they mean molecular compounds, they're talking about sharing electrons. Okay? And that's why they don't form ionic compounds, because they share electrons. Classify the following substances as a molecular compound. Well, that great slide, Jim. As a molecular compound or ionic compound. So if we look at SeO2, let's name that selenium oxide, right? Selenium is a nonmetal, oxygen is a nonmetal, molecular compound, covalently bound molecular compound. Sodium, column 1, metal, sulfur, nonmetal, ionic compound. Potassium, metal, buckyball or fullerene. So this is actually called potassium fulleride, is a metal, and carbon is a nonmetal, so it's an ionic compound, and which means it forms this big structure of 4 potassiums and 60 carbons surrounding it, and 4 potassiums built on that, and layer and layer and layer. And then we have ammonium, polyatomic anion, and sulfate. And what happens there is an ionic compound as well, even though it's composed of nonmetals. Predicting ionic charges. An anion charge equals the number of columns from the right end of the periodic table, ignoring the noble gases. So we just did that. Cation charge, number of columns from the left end of the periodic table, and they tend to lose electrons, right? But transition metals don't follow these rules. Memorize the common ones, and I don't mean memorize, what I mean is recognize the common ones, right? Silver 1, zinc 2, aluminum 3, even though aluminum is not really a transition metal. But those are common variants of those. So is that too fast? Good. All right. Nomenclature. So we went over this in lab. Formulas of ionic compounds. Step 1, identify the cation and the anion charges. So if you haven't finished that lab, this is going to be helpful, because it's going to be a repeat of what we already talked about, which is always the best way to learn something, is to repeat what you just learned, so that you are like, God, I can't hear this again. And then you're like, oh, look, that's new. Where did that come from? I heard this before, but now I've got this portion. I do that now, right? I listen to things that I already know over and over and over again, and every once in a while it's like, whoa, I didn't know you could find metals that way. Like you have a moment, an aha moment, like people like to say these days. Identify the cation and anion charges, then adjust the subscripts, remember, to balance the total negative and positive charges. Again, the subscripts represent how many of each element there are. The superscripts, right? Subscripts are the lower ones. This is a subscript. The superscript represents the charge. Don't confuse the two. Please. Keep the two straight is what I want you to do. Simple method. The charge superscript of each ion becomes the subscript of the other ion. Ah! I don't like this, right? I really don't like this, but it's true. It works. But that's how you get them confused, is you start moving them from one part down to the other. It just gives you an idea that you have to have the least common denominator. Reduce subscripts to the simplest factors. Subscript 1 is implied, not written. So let's look at that.
Just a minus.
Write the formulas for compounds made from the following elements. Aluminum and oxygen. So aluminum is 3 plus, oxygen is 2 minus. We have to have the same amount of charge. We have to balance that charge. If we just put it 1 to 1, we'd have a positive charge of 1. If we add 2 oxygens, right, now we have 3 plus, 4 minus. That'd be a charge of -1. So we need 2 aluminums, which gives us a charge of +6, and 3 oxygens, which gives us a charge of -6. Those balance out, and we're left with aluminum oxide. Zinc, for all intent and purposes, is 2 plus, and fluorine is 1 minus. So to balance that out, we need 2 fluorines, and we get zinc fluoride.
Question.
Yo.
You said you didn't like the simple method. Is that because there are some times where it's not that simple, or it just confuses?
It works perfectly every time.
Okay.
Right? But the problem comes in when you are learning and trying to differentiate between charge and the number of molecules,
Okay.
and naming and the charge, right? So that's why I hesitate to do that. Once you understand it, then I don't care if you do it, because now you're not going to get confused. Once you understand that it represents charge, and it's not just, you're not just taking the charge and putting it
Dropping it.
as the number. Right.
Okay.
And I've seen it so many times that but I still include it because it's the easiest way, and you might be able to get some points even if you don't know what you mean.
That's how I.
So in naming ionic compounds, 1, the cations. The name of the cation, or metal, element is named first, and it's unchanged. So whatever metal. If you start off with sodium, it's sodium. If you start off with magnesium, it's magnesium. Strontium, it's strontium. For metals with more than one possible cationic charge, you use Roman numerals. And again, the Roman numerals represent charge and not how many there are of that element. So chromium 3 plus, you write as chromium 1, 2, 3 in Roman numerals. For iron 2 plus, you write iron 1, 2, right, in Roman numerals. The older system used us and ic suffixes in old metal names when they exist. So for example, Fe2 plus used to be ferrous instead of iron 2, and Fe3 plus used to be ferric instead of iron 3. And again, the ic goes with the highest, what we call oxidation state, or the loss of electrons. So if you lose 3 electrons, you're ic. If you lose 2, you're us. If you lose 5, for chromium, you're chrome ic. If you lose 2, you're chrome us. Like
How
that.
do you know, for metals with more than one possible cationic, how do you know if they do or not?
How do you know which one it is?
Yeah, like how would I know looking at that metal if it has more than one possible cation?
Because, well, columns 1 and 2 don't. Transition metals do.
Okay.
And then the weird ones that are right next, like antimony does, and lead and tin do, but they're outliers. So columns 1 and 2 don't, but all the transition metals are. We find out what their charge is based on what they are attached to, the anion they're attached to. Polyatomic cations usually use ion suffix, so ammonium ion, hydronium ion. Cations in bold are the more common, and I like to use them, so those are the ones. I'm not gonna go over all of them, but, and I'm not gonna do the, yeah, never mind. I might do a classic name, like for chromium, right? Or ferric. Ferric especially, because that's still, you'll see that all the time in literature, if you were to ever get that far. So that would be the ones I know. Would just be chromium and iron, the ig and S of those two.
So question, so for last lab, there were some metals like mercury that just had a different name entirely that represented they were charged. We should just know that those names are like mercury 3.
Yeah,
Okay.
right, yeah, so you just wanna know the Roman numerals from those. I don't expect you to know like Stannis for tin or.
Yeah, that's,
Right,
yeah.
Yeah.
So if it's 10-2 Stannis, you'll put 10-2 in like per.
you'd write it as a transition node.
parentheses?
Right, with the
Okay.
Roman numerals. I won't make you know all those. I don't
Thank-
think that's a good use of your time.
It is 10-2, right, Stannis?
Yeah,
Okay,
sure.
I guess.
You have to look it up to confirm. Let's look it up to confirm. 10-2, Stannis.
Okay.
All right, you're right on the money. Perfect. So anions, the name of simple ions is gotten by, really? I put that down, gotten. Oof. You would have thought I had an education. By replacing the end of an element with the "ide" suffix. So like that was when I was doing the whole bromine, bromide, fluorine, fluoride. Okay. So if I don't take these details seriously, it's not because I don't find the material interesting and needing to be serious. I'm just not very serious. And the less serious I am about something, the more I'm into it, probably. Okay? So don't take my joking nature as not being super focused on what I'm talking about. Chlorine ion becomes chloride, right? Chlorine to chloride. Oxygen to oxide. Nitrogen to nitride. We did this already. Some polyatomic cations also use the suffix hydroxide ion, cyanide ion. But we don't call this cyanate anyway, we call it cyanide, so. All right. Oxyion anions. Something where E is a non-metal element like sulfur or phosphorus, so. And the little n represents, that subscript represents like a 3 or a 4. And then the X minus represents the charge. Don't let that screw you up. So what we're talking about here is these nice new pens. Look at how well they write too. It's awesome.
So defined.
Right, so this would be, right? This would be a oxyanion, right? Right here. Well, if I did this.
There we go.
So let's just write one that we do know. This is what we're talking about, right? Where you have 1 sulfur, 3 oxygens for sulfite, SO4, sulfate, phosphite, phosphate. And let's do the last one too. Nitrite, nitrate. So, oh, they're on here. Some have only 2 forms, a lower number of oxygen atoms and a higher number. Those are the 8s. So I just did those on the board. Phosphate, phosphite, sulfate, sulfite, nitrate, nitrite. And then 2, EON minus, where E is a halogen element, have 4 types of oxyanions. EO, EO2, sounds like Old McDonald.
Yeah.
EO3 minus and EO4 named by per, like so for perchlorate, chlorate, chloride, and hypochlorite, right? That's our other favorites, right? ClO4, perchlorate, right? And I think you should know this series, right? And that also works for bromate, bromate, bromide, hypobromite. Okay. But we usually only stick to those. We show you, we tease you with it on the lab, but I'm not gonna hold you responsible for those. So name the following, again.
Here we go.
Name the following oxyanions if you can. Phosphite, phosphate, carbonate, there's a good one. The Olin carbon oxyanion. Silicate has the formula SiO3 2-. Then we have our perchlorate, hypochlorate, bromate, iodide, tellurate, selenate, Anyway, this is the series I want you to know. And be aware of the others, but don't waste a lot of your time on it. I think I do an arsenic question on the test though, not this test. Anions forming by adding H plus to oxyanions are named by adding hydrogen and dihydrogen to the oxyanion name. So HCO3-, hydrogen carbonate ion, dihydrogen phosphate ion. The older naming system, when adding 1H plus cation, uses bi as a prefix. So when we saw bicarbonate ion, it just meant we added an H. Bisulfate ion meant we added an H. But it's really kind of confusing because it's only one and we're saying bi. And bi
Right.
usually means two. So got rid of that by committee. But it still hangs around, right? So the old chemists who still are working, we'll call things bicarbonate, but it was a generation before mine, so it will be gone, I know that. Right, you need to know that anions in the following table, for the most part, I'm not gonna hold you to that, but yeah, you gotta know HF, you gotta know the halogens, you gotta know cyanide, you gotta know hydroxide, you gotta know acetate, and then the chlorate series, and the nitrate series, and either permanganate or chromate. You need to know those and dichromate. Yeah, so all of these. Yeah.
Fun.
I'm not gonna mess with the peroxide too much because
You got that
it's
all.
tricky. It's tricky.
What do you want us to know about it? Just its name and its formula? And what-
Yeah, just be able to recognize them, right? So if I ask for the fluoride ion, you know it's F-. If I ask what's ClO4-, you know it's perchlorate. Kind of like that. So it's recognition more than memorization. Be able to name things. That's what the flashcards are for,
Yeah.
right? Okay, ionic compound names, and if you just constantly do them, you kind of know them even without memorizing. Ionic compound names, put the cation and the anion names together. The cation always comes first. In formulas, put parentheses around polyatomic ions. Name the following ionic compounds or give the correct formula based on the name. So we're going to name the metal first, magnesium, and then PO3- is phosphate, so magnesium phosphate, phosphite, excuse me, careful with my language. Al2O3, aluminum oxide, and then sodium peroxide, that's the O2. And how do I know it's peroxide? Well, I know it's peroxide because sodium's the +1, and it's in parentheses. So whenever we see an O2 in parentheses, we know it's peroxide, but don't even worry about that. Copper acetate, copper 1 acetate, right? Because there's only one copper, which means the charge is +1. Ammonium dihydrogen arsenate, there we go. There's that arsenate that I like so much, ASO4. Like, it's just like a bromate. Okay, and then dihydrogen, meaning two hydrogens, so ammonium dihydrogen arsenate. Iron 3 nitrate, which means the charge on iron is 3. Charge on nitrite is -1, so it takes 3 of them to balance that out. And then magnesium 4 oxide. Okay. And what do we got here? Naming acids. So there are 2 types of acids. There's the binary acid, which is non-metal monoatomic ion that goes into H plus and X. And then oxyacids, a polyatomic ion containing an oxygen with this EO and subscript. So let's look at some of those. Naming binary acids, hydro plus the name of the non-metal ic acid. So HBr, hydrobromic acid. Naming oxyacids, which is the other type. Oxyanions ending with 8. The base name of the companion plus ic acid, and then ike, base name of the oxyanion plus OUS acid. So nitric acid, HNO3, sulfuric acid, H2SO4, sulfurous, right, would be the ike, sulfite, so sulfurous, H2SO3, phosphoric would be H3PO4, because that's phosphate. Acetate. Yeah, you can write it either way, right? It's pet peeve. Anyway, so acetic acid, right? Because this is the acetate ion, so acetic acid. All right, finally, molecular compounds, formulas, and names. So now we've done all our iterations of ionic compounds, right? We take the name, change the non-metal to I, then we do the oxyacids, and now we're doing the molecular compounds. No charge neutrality to guide us on subscripts, so do this. Name most metallic element, the lower and or to the left, okay? So we have degrees of metallicity. Is that a word? Degrees of metallic ability. So the one lower and or to the left, so if it's below, to the left, is first, except when oxygen is combined with the halogens. Okay. So keep the first element's name, add I to the suffix root of the second element. Use Greek numerical prefixes, mono, di, tri, tetra, to indicate the numbers of each atom. So we have prefix, name of first element, prefix, name of second element, and this is only for binary compounds. So the prefix, right, if the prefix is 1, that would be mono, but we don't use it if it comes first. So we start with bi. Examples. Name a compound with 3 borons and 5 nitrogens. So 3 borons would be triboron pentanitride. Right? And what did we say? Most metallic compound is either lower. So where's our periodic table? Where is?
Do you want me to find it?
Okay, I was just gonna have you guys look it up. So we have boron, I could go back to that slide. Where's boron? 1, 2, 3, 4, 5. And then nitrogen. Nitrogen's lower, but it's not to the left, but it's lower, so it counts, it comes second. Okay. And then what is the name of P4O10? That'd be 4 phosphates, tetra, and 10 is decaoxide. If you look this up online, it will not say this, it'll call it something else. And you can either decaoxide and not drop the A, or decaoxide and drop the A. What is the molecular and empirical formulas for trinitrogen nonfluoride? So 3 nitrogens, 9 fluorides, NF39. The molecular formula, right? Empirical formula is the smallest numerical ratio between the elements, so we're going to divide each one by 3, and we get NF3, nitrogen trifluoride, which is a different compound than nitrogen, trinitrogen nonfluoride, right? So you have to be careful. Empirical formula is not necessarily the formula for a compound, and sometimes the empirical formula and the molecular formula are two different compounds.
Oh my goodness.
So explain what is wrong with the name of the formula in the second part of each statement and correct it. So SF4 is monosulfur pentafluoride. No, we don't use mono in the first word. Now, I'm not gonna do this, right? I don't. Again, this is just trickster type stuff. And I'm a joker, but not that kind. Dichlorine heptaoxide is Cl2O6. Hepta means 7, right? So we have to know that. And then these are just things to pay attention to. Again, I'm not gonna try to trick you. I don't think that's necessary. And it really doesn't do anything for your thinking ability. N2O3 is dinitrotrioxide, nitrogen trioxide. So dinitrogen trioxide. Right. So just know that the element name, in the first place, it's always the element name, is basically right here. All right, so that's that. We're gonna stop right there because I'm gonna pick up in lecture on the next subject, in lab on the next subject. So let's stop here and then we'll meet in lab in like 10 minutes. Questions? Any questions?